So continuing on the discussion, let me first share some material and then we will get into looking at the code. This is same session 14B. Just to highlight whatever we discussed, the global variables part of the process, they are all shared across the threads. Okay, this how Python maintains it, and it is the way any operating system, when we say that multiple threads are there within a process, they have the same mechanism. Okay, underneath, finally Python takes the help of OS to implement all this. Otherwise, you cannot duplicate all this implementation in the Python world, because finally what is getting executed in the CPU, only the OS knows, and only that can control this sharing of information as well as scheduling them. All that OS only can do. So effectively, all the threads that we do or create, either using threading module dot thread or the thread pool that we are going to see in the later part of the class today, or maybe if not possible, then we will move it to Wednesday. They all make use of the OS features, either it is running on Windows or Linux or whatever, and they take the help of the operating system to implement them. So, and they have a similar philosophy that is being followed by the OS, so that it can be mapped easily. So you can see that mostly what we see in the world of Python is same as what is being followed in operating systems. But there is one catch here, which maybe I will cover it on Wednesday. You might have heard about this very popular acronym, global interpreter lock, GIL. Now, why am I bringing this suddenly here? Let me tell you. We have this PVM, whatever the Python virtual machine, which is implemented in C. If we are talking about C Python, J Python is in Java. So we are talking about in C Python, and it's all implemented in C code. Now, this is nothing but a library of different code implementing all the features of thread or process or whatever multiprocessing we have, or any other implementation of the Python features, language features, are implemented in C, which is nothing but the interpreter. Now, interpreter is one thing but bytecode. So it is generating bytecodes and they are all running. Effectively, the bytecode is running on PVM, but is getting converted into assembly code and runs on the CPU. Now, the problem creeps in when we want multiple threads to run in parallel. Though you may have in my CPU, like right now what I have, has a multiple 4 cores are there. Okay, there are 0, 1, 2, 3, 4 cores, and each core has 2 hyperthreading. Okay, it can run 2 instances of threads inside a CPU core. That means they have 2 sets of CPU registers. Everything is like a twin baby. There are the 2 copies of whatever you see in a CPU. There are 2 twin copies in each of the cores. So effectively, my CPU, what I am running this Windows on, is having a capability to run 8 threads in parallel. The hardware capability has to be there. Otherwise, you can still run multiple threads, but it will be at different point in time. But when you have hardware parallelism, they really run in parallel. They run in on multiple cores simultaneously, all of them running at under some gigahertz of frequency. So they all get executed in parallel. If the hardware supports, what is the issue with the software? In the sense, issue with the Python. See, coming back to the same library, C code library that I have, they all use the Python's common data structure. Okay, Python language interpreter itself has some data structure which is implementing the language syntax and then generating some bytecodes which are executing on it. So bytecodes are generally, they execute or run operating on the data structure of the Python interpreter, right? So the Python interpreter data structure, whatever it is maintaining internally to even local variable dictionary, or you access a dictionary or a list, then it is going through something. So lot many things are happening in C, implementing the Python data, whatever your user data structures, as well as the language features are implemented in C, and they are all running on multiple cores. So the problem is, now when multiple cores are running, you don't know what stage of each execution is there in each of the cores, because there's each CPU is executing something which corresponds to some bytecode in the Python, and that Python bytecode corresponds to some data structure which is being accessed by the code. So when you have a data structure of Python which is being accessed by multiple Python programs running on different cores in parallel simultaneously, there are likely to be problems, because originally the C Python library is not implemented for a multi-threading environment, and we have multiple libraries coming in, and some data structures have to be protected, in the sense, when you are, suppose you have a linked list, a doubly linked list, and you are allowing one thread of the hardware thread to update this link, and then some other hardware thread is maybe updating either this link or maybe the same link. We don't know what part of the code they are running. So you cannot allow, when you are updating a link, you have to remove this and then connect it to something else. So there are multiple operations performed before this link is established. Both especially the double linked list, you should make sure that if you are removing one node from the double linked list, you need to update both the pointers so that it is getting connected to the other node. So it involves multiple operations which cannot be done in single instruction, and it cannot be done allowing some multiple threads to execute. So it has to be done in atomic way. Atomicity is to be taken care of. In that case, when you have multiple instructions to be executed and you want atomicity, that no other thread comes into the way before this execution completed, to make sure that this thread, this doubly linked list is updated correctly, so that it really, both the pointers are updated, so that this node is correctly removed and the other two nodes are connected together. So if it has to be taken care of, there should be a semaphore or mutex, which you might have studied in your OS course. We call it as mutex or semaphore. There should be a lock, which we call it as a lock. So when this kind of data structures are getting updated by different threads, we need to acquire the lock. That means the code which is trying to do should wait for lock to be available. Once the lock is acquired, then it is allowed to do the job, and then lock should be released. So what is the lock? Lock is another software feature which is done in atomic instruction with the help of CPU, so that the semaphore is actually making sure that only one thread executes this updating of thread data structure, maybe double linked list or any other data structure which is critical section, needs to be made sure that only one thread gets into this and updates it, and then it releases it. So there should be a lock mechanism which is to be maintained to protect the Python's data structure. So that is what is called GIL, Global Interpreter Lock. Now what they have done initially, the Python 2.2 or even 3.2, whatever they have, the latest versions, they have a GIL, which is a Global Interpreter Lock. That means any update that you do for any of those global data structures within Python, any thread performing it, they need to acquire the lock. Now what happens is, this actually puts a limit on how many threads or how you can run multiple threads in parallel, because if each one of them are waiting for the lock, effectively you are not allowing the parallelism here, you are not getting the benefit of the parallelism, because each of them will be willing, they want to update the some data structure, and they all wait on the lock. Now what happens when the lock is available? Only one of this thread will be allowed to run, the rest of it will be blocked. So it is as good as you are making it to a single threaded application, though multi-threaded features are there, multiple threads are there, because of this GIL mechanism, and which is, of course, you cannot just do away with it, because the whole Python will fail to work. All the data structures will be broken, and if you allow multiple threads to operate on the data structure. So this is putting a limit on what parallelism you can get by doing all this multiple threading. But still, there are benefits to be gained, because not all the threads are going to be simultaneously accessing their data structure. Many of them may be doing some IO. Suppose this thread is waiting for some input from the network, and then this is waiting for some GPU or some memory image processing to be done, and this is waiting for some database operation to be done by some other machine on the distributed networking or whatever. So if the task that you run, the multiple threads that you run, they're all IO based, which are dependent on the IO or waiting for some keyboard entry or any other event to happen. Suppose it is sleeping, if it sleeps for some 100 millisecond, then it is not occupying the CPU, or it is not updating the data structure, so it is just sleeping. So these, even the sleep is effectively a good IO wait mechanism, because it doesn't do anything waiting for some particular time to elapse. So these kind of operations, if the threads are doing, then actually we are getting benefited, because they can execute it and they can go on waiting for some event to happen. Then some other thread can take a control, and they can operate on the data or CPU intensive job. So even though there is a limitation because of the GIL of the way the Python interpreter is implemented, we still get a parallelism with many IO based processing, or maybe most of the tasks are waiting for some event to happen, or they wait for some time to elapse. Those kind of things, you get still better parallelism here. So just gave you one overview of GIL. Maybe you are likely to be asked about this when you talk about multi-threading to anyone, and you may explain this to convince them as well as convince yourself. This is what is happening underneath. Now, threading allows you to have different parts of your process run concurrently. Okay, this is basically that is the intent of this feature, and multiple CPUs are also there to help you. So these different parts are usually individual and have a separate unit of execution. So normally we perform different operations, and they may user level data may be different. They may operate on different data. One may be operating on student database, another one may be operating on course database, one thread, another one may be on teacher database. So they are all individual databases as far as the user is concerned. So there is no clash, there is no semaphore or lock required. So they can still go on in parallel. But effectively underneath Python world, they need to get the GIL for the Python related activities, but user level activities can still go on, and IO related activities still can go on in parallel, because they're all waiting on from events. So these different parts can be put in a process. They can be run as a different processes, or they can be run as a different threads within a process. So the process is nothing but running a program that has individual units that can be run concurrently. So how do you design your system? You design your system such a way that the multiple threads you identify, they are all, from the user level perspective at least, they are all independent of each other. They operate on different data structures, so that they don't need to acquire some lock or something at the majority of the time, but they may need to exchange some information after doing some processing. That time you can get the lock and then do it. But this is it's a design decision that you need to do when you are trying to partition your system into multi-threaded environment or multi-threaded application. So that you need to make sure that they are as independent as possible, and they perform their CPU intensive activities, and then only in a small critical regions they will do something which needs to be common across multiple threads, because there is no point in two threads running if they are totally independent. Then why are they being together in a process? So they have some common activity to be done. So they do some operation and then maybe exchange the result. So that time they can get the lock. This could be a separate lock. You can have some Python specific locks are there which you can use it. I am not. These locks are different from the GIL that I said. GIL is specific to the Python implementation, whereas at the user level also you can have locks to protect your own data structures when multiple threads are running. Anyway, I may not be spending that much time on those things, but you can, once you have this basic understanding, you will be able to understand different code and try to learn more about these multi-threaded applications and how to write them. So now we are going to first we have been seeing it threading module. We saw run. The method is executed when a new thread is initialized and it has already been started. Okay, please remember, after the start, run is called. When this method of a thread object is invoked, the thread object runs in the current context. So remember, this start is a new environment, new start, new context, but run is the current context where the start is. Okay, so I will, this you need to understand. It is run is in the current context. You remember it. When I show you some code, I will relate it to that. Okay, it's very little subtle difference is there when you start a thread or when you run a thread. Okay, they are two different things. I'll explain you with the example. Start. This method starts the initialized calling thread. Start the initialized calling thread object by calling the run method. So first it starts the initialized calling. That means init underscore init is already called initialized. Okay, and then it is starting it. After starting, run is called internally by the Python world. Join, I already explained you. This method waits for the calling thread object to terminate. We always call with respect to the object, the join. So the current thread which is executing the join with respect to an object is made to wait for that particular object to terminate. I hope this sentence is clear. The current thread which is executing the join with respect to an object which is supposed to be a thread object makes the current thread to wait till the thread object on which its join is called is terminated. So what is alive? Is alive is the method. We call it on a thread object again. It will return a Boolean flag to say whether that particular thread, what you are calling it on, is alive right now or it is already terminated. Okay, if it is already terminated, as I told you, it will be in a zombie state. Then you will get a false flag returned from this is alive function. Get name. When you call it with respect to an object, thread object, it gets you the name, which we already saw with the threading function. But you can also call with respect to a thread object also. Set name. You can also set a name of a thread. Though you set a name of a thread while calling the function, while creating the thread, you can also do it. You can change your name. Okay, we normally see the actors change their name. They have one for the commercial world and one for the private world. So you even people change their name based on different reasons. So you can change the name of a thread object after having created it using this particular method. So these are the functions which we will see now. And then apart from that, there are some more which I will explain. Then we can see the example. Get identifier. This is an identifier. As I told you, Linux has a PID for every process ID. Our Python also maintains some identifier for every thread object. So you can get that using get identifier method. Active count. This is some method which is at the threading level, gives you the number of active threads in the system which can be run. It actually sometimes gives you the number, okay, based on the number of cores you have. I will tell you with an example if you don't initialize it, but otherwise, you can initialize the maximum number of threads that you can have in the system. Then it will give you what is that, and it actually gives you number of active threads in the system. Okay, how many are running? I will show you with an example. Native ID is supposed to be specific to the operating system, but sometimes you see that it is same as the identifier. Okay, It depends on the implementation. Then thread is which we used to create a new thread. We can actually call this directly to create a new thread. I will explain you how to do this also. If you are calling a thread object directly to create a thread, then you may have to give the following parameters, which are keyword parameters. Target is the method which will be executed when the thread is created. Similar to our run, okay, when we do run, it actually run method is called when the thread is executing, right? Similarly, we can, instead of this, we can say another function which can be called. So then what happens is, if you are defining a function, my thread function, then you write it and then you pass it to this method. Then when this method ends, your thread is completed. Okay, it is similar to run call coming out. Okay, similar to that, this function can come out. So you can also give a name, a string, and daemon is another boolean keyword. When you say, you know that in C, in Linux world also the daemons are there. They run in the background. Okay, the background tasks are called daemons, and they run in the background. Now, as far as the Python is concerned, when you say false, what happens? As I told you, the Python interpreter is a process, and then in this context, we are creating threads. Suppose this thread is T1, this is T2. I make daemon of this. When I'm creating this thread, I make it false. Whereas when I make the thread T2 daemon as true. Now what exactly it means is, when this process dies, when the interpreter itself, I close it. If I have made daemon as a false, that thread will be killed. Okay. Now, what about the true? You cannot keep it alive even here, because it is with respect to the process, and the thread is cannot live without the process. So this also will be killed. Please remember, when you are creating threads, multiple threads from a process, in the normal case, these threads are associated with the parent process, and when the process dies, they don't have anybody else to, they are orphaned, and normally what happens is they will be killed. Okay, in Linux what happens is, when the parent dies, these threads, orphaned threads, will be made as a parent of, init will be made as a parent of these threads, and they still hang around, because Linux handles in a different way, but forget about it. Here, to explain about the daemon, when you make daemon true, what happens is, when you forcibly kill some threads, they will still hang around if they are happen to be true. Okay, even if the other processes are dying, and they happen to run in the background, but I have not tested it fully, so I don't want to make a strong statement. Maybe when I get a chance, I will test it out and explain you. But just have a, that, unless I see it, I don't want to go by whatever I read in the document. So daemon is a boolean flag to indicate whether it needs to run in the background or in the context of a process that is creating this thread. So when you say this, if it has to run in the background, then it will not be running in the context of the process. Then even if the process dies, this daemons will run forever. Okay, even if you kill the interpreter, they, since these threads are not running in the context of the process, they will still be running. Okay, I'm not giving any example this during this time, but if you come across some, you can share it with me. Otherwise, if I have time, I will try to write one and then share it with you. Okay, we will see. So at least to the understanding, daemon processes, if suppose you are making a thread, you are making it clear whether they need to run in the context of the process or they need to be a separate entity. Because even if the interpreter, which is the process creating the threads, still can die, the process can die, but this thread which has been created by it can still run in the background, because it is not linked with this process. So they have a separate life of their own. Okay, that is what that daemon means. And even in the Unix Linux world, daemon means it's something which is running in the background. So have it in mind as an academic interest. What is the difference between these two? And maybe we can write some code and verify it. Okay, verifying is little involved. Okay, fine. This is what the theory part of it. Let us look at some implementation. In the meantime, any questions, please always don't wait for me to ask for it. You can always interrupt me anytime. Okay, now let me show you some interesting stuff before I will stop somewhere. Okay, now this is threading 2. Okay, I am calling it as same. We are using the same threading module, so I am calling it as 1 and 2, 3 different files. Now this is some utility, PS utility, which is actually useful for getting to know about my system, where this Python is running, the platform. Okay, the platform is another library which you can use it to know about it. Now we have a similar function, same function of course. Countdown is there, and then I am just getting the PS ID, OS PID ID now here, get PID, just to tell you which PID is being used by different threads. We will learn, we will see. Okay, so this is specific to the OS. Okay, this thread is running as what OS process ID, and under which process ID it is running. We will see the output and then try to understand the output. Before I create this thread, I want to run some utility, PS utility, to know how many CPUs I have and how many logical CPUs I have. Now logical, when I make it true, per CPU how many of them are there. This, based on the number of count, it will give you the total cores. So I told you that my system has 4 CPU core, and each of the cores have 2 hyperthreads running. So this will say physical cores are 4, total cores are 8. Okay, that's the output you will get, because each of the cores have 2 logical things, and I want to measure not only the physical cores. I want to say, when I am counting it, I want to tell the utility to give me the number of logical cores I have in the system. So when I make it true, it gives me the logical cores, which happens to be 4 into 2. So it will return 8. And if you run this code on your machine, based on whether you have a dual core or quad core, you will get those numbers. Okay, it will not be the same as what you get it on my machine, of course. Now, this is an interesting API which is giving you the active count. I will explain you once I get the now output, and then I will explain you what it means. Okay, then we have other utilities, say methods of PC utility, PS utility, which gives you the CPU's frequencies, maximum, minimum, and what is the current frequency in which my core is running. So you can get all that information here. So let us run it. Physical core is 4, total core is 8, because each of the cores have 2 hyperthreads running. They have a capability to run 2 independent threads to run simultaneously on the same core. So there are 8 logical cores here. Okay, total, maybe I should say physical cores, total logical cores. Maybe I will say total physical cores. Okay, that actually makes sense. Now, active thread, number of active threads is same as how many logical cores you have. Okay, so it says, gives me 8, capability to run 8, and then what are the frequencies? This is the frequency. Okay, 1.4 gigahertz max frequency, and actually the current frequency is 1.2 gigahertz. It can go up to this, but it is running at this speed because it's based on the how much heat is generated, what is the temperature of the CPU, and then what is needed, whether it is the frequency has to be boosted or not. Based on that, the average current frequency of the CPU could be varying between the maximum to whatever minimum is. So right now it is running at a lower rate than what it can actually go up to. Okay, 1.4 is the maximum it can go up to. So I hope this is clear. Now let us get some more information about the memory that I have. I'm just exposing my system. I hope none of you are hackers, and don't pass it on to my other hacker friends you have. So I have a physical memory. This SVM virtual memory module gives me all the system virtual memory that I have. I can get the total memory available, total memory in the system, how much is available, how much is used, and what is the percentage of that is being used. So I have 1.6 gigabyte, 16 gigabytes of memory. 6.8 gigabyte is being used. So almost about 60% of it is being used, and the remaining is free, which I can use it for running some other Oracle virtual machine or something. I have still 40% of my main memory is not occupied. Okay, I have 16 GB, so sufficient memory is there, so no issues. Okay, okay. Now let us try to get some more information about what is happening when we are creating threads. Now the main thread. Now I told you that this is also a thread. I keep telling you that the main program itself is a thread. Now what is the name of that? Okay, we are not given any name when we create, when we start running this Python program. We didn't give the name, so there should be some default name given by the Python interpreter, by the language, or by the library. More specific, it's not language specific, it's a threading library specific, or the implementation specific, okay, of this particular version of Python. So I am telling how is it the threading library is getting the name. Okay, I am getting the name of this thread. So threading current thread and its name. I did not give any name. So let us see what is the name it gives. And then what is the PID? Okay, OS. I am calling the OS thing. This thread, main thread, in which process it is running. So let us see and then map it with the actual PID that you see from the OS implementation. Okay, OS interface. And then I am also interested in knowing what is the identifier that this library has given to my thread. Okay, it is a specific to Python. Please remember there is a OS specific thread running, which OS understands. It's like this. You have a nickname at home. When you come to college, you have a different name, or not a different name, your official name. When you go to your friend's place, if you're a childhood friend, you will have some different name. He or she will have a different name for you. And if it is a college friend and they have found something funny behavior of you and they have given you some new nickname in the college, then you will have a different nickname there. So it is same. This main thread has different instances, different names at different worlds. As far as the OS is concerned, the OS has given the PID for it instance, whereas when it comes to the Python world, the threading library has given some name to it, or you might have called with some name, or the thread library has given a default name for a main thread. Otherwise, when you call, you gave A, B something, so that name is different from the okay, that is name is different, and then the identifier is also different. Okay, this Python gives some different identifier compared to what the OS gives it. Okay, so let us now see this output to understand it better. Main thread is now still running. Okay, where it was also running here during this time, but now only I am inquiring it to know what its name. See this is the name. I did not give, you did not give, but the Python, when it executes a Python program in the interpreter, it gives this name. Now what is this PID? This is the OS process ID. Okay, Windows process ID 4648, whereas the thread identifier for the same thread is 22012. So this is unique to thread, unique in the Python world, but this is understandable in the operating system world. Now let us now analyze whether this PID is different from the interpreter's ID or not. Now I said this interpreter is running. We are running this code in this interpreter context. Okay. Now I am going to already import OS is done. So I think I don't need to do that. Now if I do OS get PID, here I am executing it on the interpreter's command line. Then it is giving me what is the PID of this interpreter. Now, when you ran this Python program, inside that you got the PID here, and what you get here also is same. That means what? This process is running in the context of that particular instance of interpreter. Now, suppose if I create a new console, okay, let me try that. I'm creating a new console. This I have not imported the OS. So if I do os dot get PID, it will say that I don't know the OS module. So I need to import here, because this is the new instance of the interpreter. os dot get PID. It says 19384 is the PID. Now remember, this was some 4648 and this is 1934. 384. It is same as like Windows. Oh, sorry, Linux. Linux also allocates PID in the increasing number order. Okay, as the new process gets created, you get a higher value of PID as you keep creating new threads. Okay, new processes. So I think Windows also is following. I'm not very much aware of what happens underneath the Windows, but effectively all the operating system follow the same convention, that if you want to know which process was created first, the quick thing is to know about the value of the PIDs. If it is smaller, it was created earlier than the one which is with a larger value. Okay, now you know that this was created when I in fact started in the afternoon. Till then, this maybe I don't know, in sometime in the middle, 23 is coming here. So somewhere I killed all the consoles, and it was way back. Okay, sometime. Now by the time the process Windows has created so many processes, and it would have killed. Not that all the processes in between them are living now, but they might have been created and killed. But even we did that multiple times, programs we ran, but PIDs keep changing, keep increasing. Okay, it's not that all the processes are alive and they don't reuse the PID which was used recently. Okay, they keep allocating new higher PIDs, and it keeps on going. Now, what if I run this code with this context alive, okay, active? Now let me run this code here. Now you see here, this code is starting a new cell, a new interpreter, and then it is not the same one what we saw. This is 1984. Now this is identifier is different, but this is same 19384. That means what? This is running in the context of this particular interpreter, and I get the same ID. But now this process is running on this interpreter also. It ran. Now it is not. Now it has come out, and it ran here and came out. It had a different PIDs. Okay, remember that. Now both the consoles are running. Okay, both these interpreters are active and they are running. Now these two PIDs, I should be able to see it in my in the Windows Task Manager. I should be able to see processor. These are all processes are there. Now where are the IDs? Details, PID. Okay. Now I don't remember the number. 4648. Okay, let me order it in this way. 4648. Our friend is somewhere here. Yeah. See here, this is the executable Python exe. Okay, and nothing but the interpreter. Okay, this 4648 interpreter. Now what about this front? Our another Python interpreter 20980. We need to go down 20. Sorry, 980. Oh, what happened? I don't see here. What happened? Let me see. Oh, sorry. I'm looking at this thread identifier. Sorry. This is the PID, right? 19384. Okay. It will not bluff. 19384 should be there. Yeah, it is there. So this is the process ID. This is as far as the Windows is concerned, this is the process. Okay, so I hope this is clear to you. Now let us go further. If there are no doubts, I hope so. Now let me execute something more. I am going to create a thread now, and let me put it here. We saw that earlier it was giving me, I'm going to run it in this context only. I'm going to create a thread. Now thread A is created and the active thread is still 8. Okay, now it is only created, it is not started running yet. Okay, we have not started it. Now I have created it, and then now I am going to create this guy, thread B. I'm going stage by stage so that you don't get overwhelmed with so much of code coming into the way. So I'm creating creating the object. Okay, please remember, I'm creating a thread object. I'm not running it, I'm not starting it. Thread B is also created. Okay, the object is ready now. Now I can start one by one. So let me take the whole thing. I start it and then count the number of threads. So let me, now what I'm going to do, I'm going to start the thread, only thread A. I'm not starting thread B now. Thread A is started. I'm sleeping for 0.1 second and then printing the active count. Now when I start the thread A, it also calls run, I told you. So it is going to print this and it is going to print the PID also. So I want to see whether this PID is same as the PID that we get here. Okay, this is still continuing to be 4648. Okay, earlier also 4648. Remember, it continues to be 4648 this instance. So I want to see when I run this thread what PID I get from the OS. Okay, in that context, please remember, when I am executing this OS get PID, I am running it in this context, but it gives you me the PID of as far as this process is concerned. So I'm calling it with respect to that object. So let us see what happens. Okay, I'm going to run it. Let me clear that off all this output. So that now what have happened? We have created both the threads, but only starting the thread A now. Now thread A started running and I gave a small count, I think. Let me see what I created it. Thread A, I'm calling my thread A with a name. So self name. I removed all the unwanted things, all the delays and count and all that. I have actually made it simple. Only it is going to count twice and then stop. Okay, I made some small changes so that we remove all the clutter. So what happened is it counts for 2 iterations and then stops. Thread A is finished. But during the thread A starting, it prints the PID. Okay, within that, it's also getting the same 4648. That means this thread is also running in the same context of the original interpreter process. So that's what I'm trying to tell you. These threads are running in the same context of PID. PID is nothing but the process ID as far as the Windows is concerned, and the thread identifiers are different. Okay, this 7048 is a thread identifier for thread A. Now when I start the thread B, you will get a different thread identifier for it. Okay, let us see that. I hope so far you are with me. Now I am going to start the thread B also. Okay, and I am going to print its ID also, the identifier. Let us see whether they are different or same as the A. So I'm going to start the thread B now, and then I am again sleeping for a while to get the outputs. Okay, so that they don't get mixed up. Now you see thread B is also counting twice and it is also finished. Okay, thread B counted 2 and 1 and they finished, and A also counted 2, counted 1 and finished. So they are all happening properly. Now what is the identifier? This thread B is printed the identifier as 3768 and thread A printed this as a 2348. Okay, so thread identifier doesn't follow this increasing number concept. Okay, don't mix it. PID only follows that concept, whereas thread ID is some implementation specific thing which I don't think any documentation says about it, and at least I did not come across it. So some identifier which is uniquely identifies a particular thread instance. Okay, so both these thread instances are running in the same process, which is from the OS perspective, its PID is 4648. Okay, and what is the number of active counts? Now you see here, it is increasing. Threads active so far was 8. Once you start the thread, it is increasing. When I start another thread B, it increases to one more. Now if I, after stopping, if I come to know or find out what is the active threads, then you will know whether it comes back to the old value or not. So let us, oh, I think I have seen that. No, this 5 is, oh, 5 is printed much before these threads were ending. So I need to sleep for a while. Okay, let me sleep so that both threads get completed, maybe 3 seconds. And then let us print now how many threads are active. Let me write it as 6. I hope you are following me what I am trying to do. See, this was printed while the thread A and B are still alive. So you got 10 there. Okay, both of them are alive. Now I am trying to wait for a while, sleeping for some time, so that both thread A and thread B finishes, and then this print is coming out. So I want to know whether this comes back to 8 or what happens to the count. So let us see. Both are there, both are finished, and now this printed after some delay. I allowed the both the threads to finish its job. Now it is coming back to 8. Okay, so this 8 is based on the number of CPUs and threads I have. So it gives me that it is actually making use of those 8 cores, logical cores in the system, maybe to run their internal things. Okay, the Python may be internally making use of that. That's why you see that the active threads are 8 now. And then what I have created is going and coming up and going off. Okay, now this is already you have seen. So let me go up to this. Join I already explained, so I don't need to repeat it and bore you. But just for the completeness sake, let me tell you, it is waiting for thread A to join, thread B to join. You know that by now all the threads are died. Both the thread A and thread B have exited, so they will come out easily, and then they both will fall through. Otherwise, it will not get blocked here. What I'm saying is, it will not get blocked here, and it will come down immediately. So it immediately comes down because both of them have finished before even you called join. So what I'm saying is, you are free to call the join anytime, because you don't know when you call the join whether by the time the thread A's are alive or dead, you don't know. So the main thread is not aware of it unless it is waiting for it. So now it is saying I want to wait to know really the thread A's are still alive or not. So it comes out immediately when the thread A is done. Okay, that's what you see here. Now I am going to show you something interesting. I am going to call thread A run. Please remember, once the thread A object was created, then I did start. Okay, I did a start. Both for thread A and thread B, I did a start, which internally called run method. So this start can be called only once when you create an object. Yeah? Once you create a thread A object, once only you can call a start. If I call another start, you will get a runtime error. Maybe to demonstrate that, I will write thread A start. I can't start a thread which has already been started. It's like your two-wheeler, when you start again, it will give you some funny sound that a machine is already running. Even the car also, it gives you, you cannot start a car which is already started, right? So you cannot start a thread which has already been started. So let me try to start it. What do I get at the end of it? Runtime error. Threads can only be started once. So I need to comment off this. Okay. Now I can, but I am free to run. I am free to run or call the run method multiple times. Once the thread object is started, I can run again. So main is going to call the thread A now. Now there is a difference. This thread A is running in the context of, okay, everything is running in the context of the process, but here you cannot have a parallel thing running. Okay, as far as the Python is concerned, it doesn't come down until the run is completed. Okay, you remember when I say this run is different from this start we did earlier. When we did the start, it branched off to that thread and then it came down and printed something, and then you saw that those threads were running in the background. But when I start it here, when I say run here, it will not come down to the next instruction until the thread A completes, when until the thread A terminates, or when the run method is exited. So to demonstrate that, I will put, I say thread A run, and then I will copy this also to show you that it doesn't come down to execute this until this thread A completely prints to countdown and thread A finished. Till then you will not see this print. Okay, so let me, okay, this let me call it as 1 dot and then 2 dot. Okay, to just say that we know the difference between these two, and let us run it. Now what I'm doing, once I ran thread A and thread B started and then completed it, and then I restarted the thread again. This one is coming here. I restarted the thread A again. Okay. Main is calling the run method directly, not the start, because start you cannot call. We tried to do that and it failed. So I started running run. But this print main did not come until the A finished. Remember, this was not the case when I started earlier. When I say start, it came down, it printed even this while the thread A was running. We saw that the thread A output was coming and this main thread A is started. Okay, and we printed this count and then we thread B started. Okay, you can see that if you want. I already explained it, so I don't need to explain it again. Thread A, say thread A started, main thread active now is printed, and then thread A was running. Okay, it was, while it is running, I already went ahead with the remaining things. I started off the thread B also. So main went ahead with the remaining instructions when I started this thread A and thread B. Whereas when I do this run, it doesn't go further. It waits for the run to complete and then comes down. That's why you see that here, after thread A finishes only, it prints this and then starts the main, again run thread B, starts it, and then that gets finished and then it comes down. Okay, so see the difference, subtle difference between these two. Okay, and then I will show you this to just conclude it, that this will also be printed only when the thread B finishes. Okay, so and then you will get back the active count back to 8. So with this try is done. Okay, so main is also printing only when the thread B is finished. Okay, that's what I wanted to highlight. Now we are at the, what do you want? You want a break and then 1 hour, or maybe continue with early finishing of the class. Maybe I will continue. I will complete the threading related things. Okay, thank you. Because we are all almost in the break will actually make us forget what we are learning, at least for me. So let me continue with that. So I think this thread is run, and this I don't want to do it because, okay, I'll copy paste for the completeness sake, but we have already tried it. I've written some comments, so it will be useful for you when you look at the code. That's all. So this is done. So let us start with the try 3. Mostly that will be a smaller one, I think, compared to this. We can finish it fast. Okay, I hope this is clear. Okay, now I will close this guy, I want to start a new one. Save as. Where are the class? I don't know. Where did I save it? Where did it? I don't know where I have saved. I have to restore it back. Okay. So let us do it here. Not in. Sorry. I should have saved it here. Okay, I don't know. Okay. Now let me try where it is actually before I forget. Ah, oh, session sample program. Oh, it is lying there. Okay, I will miss this guy, so I will save it in a place where I want to be. It's a default directory I given, so I got back here. Okay, fine. Now this is a very simple code, so let me take the whole thing and then explain you. Just to demonstrate different methods of threading. Here also the same count is 5 and 1, and so it is running for a while. Same thing. What I am trying to here is to explain you this is alive. Okay. Now when I do a thread, my thread and then thread A, I'm just creating the thread object. I have not started the run. I have not called a start. I am doing it here only. So if I ask whether the thread A is alive, it should give me false. It's not alive. Its object is created, but it's not running. So I should get false here. I should get the name what I have passed here, AA, and then I am setting the name to AA. Then I get the name. It should become AA now. Okay, if I print the name, it should become AA. Then I start it. Then I am asking, is it alive? Then it should give return true. Then I am calling thread B sleeping for a while. That's all. This program doesn't do anything else other than just demonstrating the calling of is alive. Okay, and how it is relevant to the starting of the thread. So because the count is 5, it is going to count for 5 times. Now let me explain. Thread A was okay. It is done now. Finally, I changed the name. Initially it was A, and then I set the name to AA. Then the new name is AA. Starting the thread AA now. See, internally also it is printing the AA. So the same variable is getting affected, and you are getting the reflection here. Okay, AA is the name is changed. Now, is thread alive? Before I started, it was false. After I started, it is true. Okay, and then I am creating a thread B. Creating a thread B, but I am not starting it here. So it's okay. I can remove it or let it be there. Okay, you can modify it, make some changes, and play around with this to learn more about it. Okay, this is to just demonstrate some of the functions which are there in the threading module. Okay, so this is done. This is done. So let me now start a new file for the new savers. For okay, now what is this function? Okay, not much. Let me tell you some more interesting stuff about the threads here. Okay, this is a little different. I am calling a method. Okay, I'm not having a class like what I have. Okay, sorry. Oh, I don't have the previous code. Okay, let me open the previous code so that you also know thread 0, thread 3. Okay. here in thread 3, we were actually using the class which is inherited from the thread, and then calling or starting a thread was using the creating a thread object and then calling the start. This is how we were creating the thread. Now I am showing you another method of calling a thread or creating a thread is directly creating the thread object from the threading module. Now if you are doing it, you need to give the target method which I explained in the PDF, and then the parameter can be passed directly and then a name also, then it gets created. Now once this thread object is created, what we do, I'm checking is it alive or not. Okay, and what is the thread object itself doing? It is printing I have entered the thread object, I am getting the native ID, okay, and then it sleeps for 2 seconds and then terminating. So this method is not calling any countdown or anything. It's just a method just prints the native ID and then its own ID, which is ID is whatever I am passing, actually a parameter. It prints that thread 1 and thread 2, and then it sleeps for 2 seconds and then comes out. Okay, now I am checking whether thread 1 is alive. Now the question here is, will it, after this is created, will it execute this immediately? Because it is going to sleep for 2 seconds, right? Even if it goes there and execute this instruction, when this is sleeping, the main thread can continue further, and below this it should be printed here. We want to see whether this, after the thread 1 was created, this print is coming while this guy is sleeping or after this thread is done. Okay, when the thread ID is terminated, then only is it coming or not. So I want to just show you how does it behave in this case. Okay, just run it. Maybe to simplify things, let me not keep it here. Let me do one thing. One thread only I will create. Okay, 2 threads creating together is doesn't serve the purpose. Too much of code. So let me just start only this. Let me print it. Now you see, it printed this native ID as something, and then it was waiting there. And then thread 1 ID is terminating. Then only after the thread 1 was created is printing. That means the main thread is not going further. It is similar to calling the run method in the earlier case. That is, this thread function is executing in the same context of or the same thread, okay, as this guy. So it finishes. It's like more or less, you may wonder that it is like a similar to a method function or a function call, but it's not as bad as function call, but it is in the same context it is running. That's why when it is sleeping, the main thread is not coming and then printing it down. It is waiting for it to complete and then it is coming down. Okay, it is equivalent to calling a run. Okay, so understand the difference between these two. Okay, starting using the class and then starting the thread is different from creating a thread like this and making it run. Okay, so let me complete the remaining thing. I wanted to just demonstrate this so that you know the difference between these two. The previous code is okay up to this point. Okay, and then what is the alive? It is not alive because the thread is already, one is terminated, so it says false. Okay, that's what. Now remaining code, say I am just printing it now. Okay, now thread 2 delay. After I come out, I sleep for 2 minutes, this 2 seconds, this main thread actually, and it is calling the thread 2. Now this also will go there and it will get blocked for 2 seconds, then comes back and prints this, and then it will also say that I don't see that the thread is alive. It will say false. Then count will be printed. It will be same as 8 what we saw. Then I am printing some more additional information about what is the PID of this. It's same, like nothing different actually. identifier. Maybe I can remove this to unnecessarily. Okay, okay. I don't think it is adding any new information, but it's no harm in being there. I'm printing the stack size, which I have not told you earlier. So let me show you the output, and then we will be done with this. Now it is waiting for 2 seconds in thread 1. It comes out. Then thread 2 is waiting now 2 seconds, and then comes down. Now these are all some different values of internally what you see. Okay, timeout max and other information that you can get it from about the thread. And this is just a thread, main thread object. It's okay. I don't think much information is here, but this is same as the PID of this particular interpreter. Okay, so just to summarize, this I showed you to creating of another thread using this target and name. There is a daemon also is there as another parameter, true or false you can give, which is actually running in the same context of this thread. And when this thread is completed, it comes down and then executes the remaining thing. Okay, that's what I wanted to show you here. Any questions here? Nothing. Okay, let us go forward. So this is done. I think I have two more to show you. Let me open that. Anything new here? I don't think. Wait a minute. I'll just. Yeah. Something is new is here. Okay. So let me save this. Five. Okay. Now this code can be directly taken. Very small piece of code, but small changes there to show you. Now, what is the difference? I am going to call the same method. Okay. My thread and thread 1. Only thing is I have added this while true pass. So what happens here is this thread will run forever. Okay, and you will not see anything. This will not come out. Okay, it will run. This will never be printed. That's what I wanted to just demonstrate. It's nothing great, but still you should know that you can make as a thread get into an infinite loop. So it goes here and then gets into a while loop. It is same as a even method function. Method, if you function call, if you make it and then it will never return. So here the thread doesn't return. So it doesn't come down to the main thread, and you will see that this is in an infinite loop forever. And if you want to kill it, there is no way until you kill this particular instance of the interpreter. Okay, that's all I wanted to show you. Now let me save this guy as 6 now. One more. Save as only I did, I hope. So this I'll close it. This I will delete. So one more. I hope this is little different. So let me explain this code. I'm going back to the old method of creating it, I wanted to show you some multiple threads running in parallel, and then I wanted to differentiate between local variable and the global variable, which is being maintained across the thread. Okay, now let me explain. I am using the same myThread class with the thread function getting inherited. This class is getting inherited, and then we call the run method. Now I am using a local variable just to demonstrate the fact that each thread is maintaining its own local var. Okay, so they will have different values. So what happens is when I create thread A, B, and then something other than thread A and B, they get into this if conditions and do something different. But they all execute the same run function. They all come in with the same entry point. and then they take a different path inside, and then they come here. And why did I say this is never executed? No, that's not true. Yeah. Okay, that's true. I'll tell you. This is not inside the while loop. Okay, this is not inside the while loop. So it is a while true. What I am making is each of the threads I create, they are going to live forever. Okay, they are going to be running forever. But each thread is going to be sleeping for different time. One thread A is going to sleep for 5 seconds. Every 5 seconds it is going to wake up. This guy is going to wake up every 10 seconds. And then if the name is not A and B, that thread is going to be waking up every 20 seconds. Now, is it going to terminate? They are not going to terminate. All the threads are going to run forever. So this is never executed, which is a exit of this function. Run is not going to be exited at all because each of them are inside the while loop. Even the else is also in the while loop. Else if is also in the while loop. Everything is in the while loop. Now, I want to demonstrate the local variables are getting incremented once in 5 seconds here, whereas this is getting incremented once in 10 seconds and this is getting incremented once in 20 seconds. So these threads are running at a different frequencies and they increment their own local variables at different point in time, and this is done more frequently than this and than this. So you will see that this value what I am using as an index here, 1 dot something, 2 dot something, is going to be incrementing based on the frequency of these threads. Okay, they are going to be maintained individually. So I wrote this code only to demonstrate that each of the threads are going to maintain different local variables, but they are all running in the grand you know uh, namespace of this main thread, main process. Okay, so thread A is created. I'm starting it. I'm not having any delay here because they are just going to run forever. Why should I delay here? I'm creating thread B, starting here. I'm checking everything after they are started. I'm checking whether they are alive, and then I'm creating a thread C. I'm checking alive, and then this itself is going to a loop, a sleep. But main thread is going to the sleep, but the thread A, thread B, and the thread C are running in the background, and they are going to run forever, and they are going to print this message with the incrementing index. That's what I want to show you. Okay, so just to see that they are all running in the background and our main thread is sleeping nicely. So since 5 seconds, 10 seconds are little longer, you will see that they are taking more time. Okay, now there will be some overlap of these messages because of the way it is getting printed, but you see here thread A is counting its prints 2, 3, okay, 4. Thread A is incrementing. Similarly, thread C is incrementing 1, sorry, 1 here, where is it? Okay, 1 here, then 2, and then when thread C comes next, it will have 3. See here, it comes 3. So different index is coming for different threads. That means the local where they are maintaining is different copies. Each of the threads are having their own stack and their own local variable, and they are all running in the context of the main thread, and they will be running forever. Now let us see whether this main thread has woken up or not, because 20 seconds has elapsed multiple times. So main thread should have opened. Where is it? Yeah, main thread has woken up after 20 seconds and it has come out. Okay, but these threads are running forever. They are all running. They are created by this thread and they are running. Okay, it has come out. The main thread has come out because I am able to get the interpreters is responding to me. I can run some command here. Okay, let me try this. You can see that what I am doing, I just thought I will do this. Some command problem. Run command. Run. I think I need to call. I forget then. Run cell is different. I forget. Run I can do. I'm missing the syntax. Oh, not found. Maybe I should this a current dot. I don't know. I forget the syntax. Okay. No, I don't forget. Okay. So now what is happening is this thread will all the threads are thread A, B, C are all running in the background. Okay. In the context of this particular interpreter process, if I want to kill them, only way to kill them is killing this Y. Actually, I look for the kill method. Okay. They say that Python doesn't have a terminate, but process has a terminate, but thread doesn't have a terminate or a kill method. So, okay, if I come across, I'll tell you. So this I have now terminated them and it is done. Okay, this thread is done. So with this, I wanted to, whatever I wanted to show you on threading is done. Threading module is done. Shall I continue? Maybe I should. With thread pool, they are not too much, but simple only. I want to ask you guys whether I'm just having 10 more minutes. Do you have some more energy left? Okay, thank you. So let me start off with thread pool. Okay. Maybe I will not explain too many things. I will, as I promised, maybe another 10 minutes, 15 minutes, 20 minutes, not more than that. Where is it? Okay. It's a different concept. So okay, this is wrong. 1 second. I will call it as TP1 and TP3 maybe, thread pool executor. Okay, maybe 3. Okay. Better to do it before I forget. Now, what is thread pool? Thread pool is having a pre-created threads. It's like a template. Okay. We have multiple threads already created and ready. Okay. In a pool. Then, whenever you want to run a function, okay, some function, thread function, you take one thread from the pool if it is available and then run it. You use it using submit. Okay, you call it with the submit function of thread pool and then you run it. So it is same as the threads running in the same context, all that are same. Okay, except that you are not doing a create and then calling a start. Here this step is removed, which is already been created and kept. It's like buying a cloth and then stitching it for you. Okay, buying a cloth and stitching it for you. Here we have a ready-made cloth. You go there, take a particular size which fits you. You come out from the shop with a dress ready. So it's similar to having a ready-made threads available to you. But only thing is you may ask the tailor to maybe stitch it little bit. It is tight, maybe loose. You know, they do some small tinkering there. It's the same as maybe giving a function for a thread and then making it run. So it's like a Ola cab maybe. Okay, instead of buying a car, you have a Ola cab. You take it, run it, and submit it back, give it back to them, and that's all. Your job is done. Instead of owning your own car, you are using a Ola cab or so that's a similar good example maybe instead of a tailor. So in Python, a thread pool is a group of idle threads, pre-instantiated and are ever ready to given a task. Okay, to be given a task. So they are always ready, waiting for you to give a job. Okay, it's like contractors waiting outside the company. You, whenever you want to get a new job to be done, you get a contractor, use them for a month, and then you know tell them that okay, job is done. So we can either instantiate new threads for each or use okay, we can instantiate a new threads for every use, or use a thread pool for new threads. Okay, you can recruit a person or use a contractor, or you can buy a Ola car or buy a car. Okay, that's a difference. Okay, actually this saves a lot of time in terms of creating the thread, and you have a ready-made thread available to you. You can just use it and keep it there. But one thing you have to remember, that you are maintaining this many threads in your pool always. Okay, it is going to occupy some space, memory, but it may not occupy CPU time, because if they are not running, they are idle, they are not going to occupy the CPU. Performance is not going to be affected. But when you want a thread, it's available to you ready made. So that's the advantage you get by using the thread pool. But when the number of tasks is way more, then Python thread pool is preferred over the former method. So when you are creating many threads, you cannot instantiate it every time. So better to have, see, suppose your application is such that you want some 10, maybe 100 threads to be run for a while, and then maybe you do something else, and then you want a spike of threads to be created, run. So in this case, it doesn't make sense to create thread, delete all of them, and then again create thread and delete all of them. So what you do, you keep the, maybe may not be 100, maybe less than that, keep it ready in the thread pool, use them. You know that maximum you may need 100, so you can even sometimes you may be average, you may do 50, then thread pool can be 50. So you can use it. If suppose you may wonder, you may have a question that if suppose I need a thread but it is not available in the thread pool, don't think that it will be denied. Okay, you can still create a thread using the normal library call. It, Python does it for you. You don't need to worry about it. If it is not available in the pool, it just creates a new thread for you and gives you. Okay, so you are not actually affected by running out of thread. Okay, it's like it's transparent to you. So you are getting the benefit of having a pool of thread. But at the same time, suddenly if you need a spike of thread requirement, then Python handles it for you. So you don't even know whether it is coming from the pool or it is coming outside of the pool. Doesn't matter. Okay, so it is possible. So a thread pool can manage parallel execution of larger number of threads as follows. A thread can be reused if a thread is in the thread pool completes its execution. So suppose you have taken a thread and then given a function and it is executing, and when it is terminate, it comes back to the free pool. So it can be reused. So same thread template or object can be reused without you trying to do lot of programming. So it is a, actually is a like a helper function, giving you, you don't need to do many of the jobs of creating threads and other things, which is available as a pool, and use it and throw it. Okay, that's the advantage of having a thread pool. A new thread is created to replace a thread that is terminated. So thread is when I saying is this thread is terminated, then it is actually created inside. Okay, you are not, don't think that okay, this thread I took it from the thread pool and it got killed, do I now lose the thread inside the pool? No, it will be replenished. So background it is done not by you. Okay, and then when you ask for it, it is available to you. So that's the beauty of thread pool. I hope this is clear to you. This is actually a concurrent futures. This is the module, and what it returns is a future object. Okay, it contains a concrete subclass known as thread pool executor. Okay, this is a main class, and then thread pool executor is a, subclass. Uses a multi-threading. Okay, which gets you a pool of thread for submitting the task. I will explain you with the code, which is easier to understand. The pool thus created assigns tasks to the available threads. Okay, pool thus created assigns tasks to the available threads and schedules on them. So you can, when you submit a job, The pool takes care of scheduling the thread, running it, all that is done in the background. You don't need to worry about calling a start, calling a run. Those things are not there. Okay, that is the advantage of this thread pool. So we have another 10 minutes maybe I will take to explain you with the example code so that you get to know what I am explaining as a thread pool. Okay, then we will close both of them. Open thread pool. I call it as thread C. So let me. So to save time, I'm not going to do copy business. We will run it in the same file. Okay. Actually, it is not even try is not there. So I can give you the same code to you. So actually, there is one nice write-up, Jason Brownie. Okay, if you guys know him, he's very active blogger on Python. Jason Brownie, look for him. He is very liberal in accepting the request also, and he is good coming up with lots of blogs on thread pool. Right now he is doing it, and then he writes a lot many things about Python. If you are very, of course, all of you are going to be spending your maybe another 10 years at least on Python before some other language comes into takes over. So this blog following him will be good. Lots of good writes up come from him. So I have put that so that you guys can get benefited. Then I'm getting it from here, importing the thread pool executor class from this futures module. Then maybe you can refer this also, but I don't say this is a very authentic than what Brownie writes. Now platform uname, okay, something which if I thought I will give you some more things, system related things, platform related things, I thought I will print it for you. This is very trivial. You can see that. Coming back to our interesting thing, thread pool executor, you are creating it. Now, when you create a thread pool executor without any parameter, it is going to create some number of pools in it. Okay, let me explain a little bit. When I'm creating a thread pool executor only, the thread pool is created. Okay, TP is created. Now, how many threads will be there in it? That's a question, right? You are not giving it. You are having an option, configurable option to say how many threads I want in the pool. But if you don't give, it is going to look into your CPU. Okay, your CPU. And then it says in my CPU, there are 4 cores, each of them are having 2 threads. Then it knows that there are 8 logical threads are possible to be run. Then it is creating a thread pool, which is the number of thread pools that you have, logical thread pools that you can run in your system, plus 4 is what is created here. Okay. See, you cannot create a thread pool if the user has not given, then it should have some logic. The library should have some logic to create it. So they have used this business of comparing it with the logical threads that can be run in a particular system where this program is running. And then they added some plus 4 because not all the threads are going to be alive all the time. They are going to be waiting on some event or sleeping. Then having more gives you a flexibility to create more threads in your application. So, but not giving much more many will be not good. So they have made it some plus 4 and then given you that. So that is what I want to demonstrate here. When you don't give a parameter. Now when you give max workers is the keyword where you can say I want to create 100 threads, no problem. It gives you, okay, not that all of them are going to be running in parallel, but it gives you the flexibility to run or create a thread pool of that many number. So the CPU count is 8, the max workers is 8 plus 4. Okay, when you do not give a any parameter to the thread pool executor, it is going to create a maximum logical threads you have in your system plus 4. Okay, that's the logic they have used. And then when you give 100, it is going to print 100. Okay, then you can print it actually using the underscore max workers executor object. You can print it and then you can shut it down. Okay, just I'm explaining this using only TPE, Max Workers, this program. Now I'm going to create a thread. I hope this is clear to you. Now I'm going to create threads using this. Okay. I'm using two functions, count number of words and count number of characters. Okay. And then what I'm doing, these two are functions. Okay. I created an executor. I wanted only 4 threads to be created. I don't even want the default of 8. Then I'm giving some sentence, and I need to give 2 parameters when I'm submitting it. I told you that I need to submit a function to execute and the parameter to be passed to the function. Okay, always. So I am here passing only single parameter. It's a tuple. Okay, always the parameters are passed as a tuple. So you need to put a parenthesis around it. I think I need to put a comma. So to be I don't know. Let me put a comma here. Okay, I didn't do it anywhere else. Okay, fine. It will handle it. So what I'm doing, I am creating a pool of 4 threads and then submitting a job. When I submit a job, I won't say which thread I want to submit. It's like a freelance, whatever available, it will be allocated. If there are no thread available, it will be taken outside of the thread. Okay, a thread pool. So it creates a thread on, and then that's all. Once I do this, it is running. Okay. Once I submit it, I don't need to do any of those things what I did earlier. It starts running. What is it running? It is running this method, which is counting the words of the sentence that I have passed. Now, what is the function doing? It is getting the length of the words, number of words in it, and sleeps for a minute, then prints it and comes out. It is not running forever. It's just maybe sleeps for a while so that I get a feel of the time, and so that I can create some more threads here. So I am intentionally putting a sleep here, and then another function is counting the number of characters, and then it sleeps for a while, then it prints it and comes out. So these threads are short-lived threads. So thread pool can be used for a short-living activities which are to be run in parallel. Okay, good example could be, okay, so if you want to process a particular file and then maybe process it and then output it, you can use it, thread pool, you can use it. Okay, I want you to use it for your real scenario application. In case if you are having a multi-threaded core in it in your system, you can really see a benefit of this thread pool, and that's why that's the reason I am teaching this, so that you will be able to feel comfortable to use it. So I submit the job, that's all. That function is executed, and when it comes out, you don't need to catch it or something. It will join and all is not needed. This thread will go back to the thread pool and it will be completed. Okay, that's all. So I am creating it and then running them, and then I am checking whether they are done or not. Then I am sleeping for a while. Then I am checking again. So it goes on. Okay, so let me run it and then explaining you the code so that you understand what is happening. Anyway, I will be sharing this code. You can also run it yourself. It's not a difficult thing to understand once you have understood my explanation. So they all run. Now see here, I will highlight. Okay, let it complete. Let me show you what I have done. I have created the executor pool with the 4 threads. Okay, and then I am creating thread 1, thread 2 with the words and character function, different function, and then I am using different sentence I am creating, and then again calling thread 3 and thread 4 with these 2 methods. So they are going to run in parallel. Then I am creating another sentence 3 and then calling thread 5. I am also calling it such a way that this thread and 1, 2, 3, thread 1, 2, 3, 4 are not yet done yet. Okay, because the number of threads are more, number of words, it doesn't matter number of words, but sleeping is more. Okay, they are sleep for a while. Okay, 1 second and 2 seconds. By the time all the threads are created, what happens is I am calling a thread 5 create, okay, submit, before even all the 4 threads have exited. That means the thread pool is run out of the threads. Now what happens? I wanted to check whether when the thread pool is still not having any threads available, if I call the executor again, on the executor only I'm submitting a new job, then it doesn't say no. it knows that the thread pool is over, but it is creating a thread outside of the thread pool, doesn't matter, and gives you that. Okay, and then you can still run it. Okay, and you can see that it successfully gets completed. Okay, thread 5 is also get a job. Okay, where is thread 5? This thread is thread 5. Okay, ABCD, capital ABCD is the thread 5. The thread 5 is having this string, so I am able to run it. Okay, that's what I wanted to demonstrate. Then executor is shut down. Once I executor is shut down, okay, I cannot call it on that. Okay, runtime error will happen once the executor is shut down. That means the thread pool is no longer valid. I have to create a new executor and then run it. Okay, that's all I am demonstrating it. I think this code is self-explanatory, and unless you have some question to ask, otherwise we are done